one, the University of Connecticut. She's visiting with us for all of this week, and for the first couple of days of next week is part of our visitor program, the first in our visitor program. She took her PhD at the University of California at Berkeley, has done postdocs, let's see, National University of Singapore, Fields Institute at University of Waterloo, Dartmouth, and the University of Connecticut. We have known one another since she was at Berkeley. She'll talk about randomness and computational strength, and we look forward to hearing what you have to say.
Thank you, Leslie, for the introduction. Thank you all for having me here as part of your visitor program. I have spent a week at Carbondale before, as some of you know. In that week, I was approximately 12 or 13. It was an enrichment program for middle school kids, and the main thing I remember is running around, making new friends, and packaging eggs very nicely so that maybe they wouldn't break if you dropped them off the balcony as part of an engineering program. I'm delighted to be back in a slightly different capacity now, even though I still probably can't package an egg to survive a fall from 2 stories up. So, all right, so I'm talking about randomness and computational strength, and I think I'm going to start out by presenting you with some initial segments of infinite binary sequences, and I'm going to start by saying, which of these look random? Well, clearly you can't be sure because I've only given you the first some bits of them. And for all you know, they're all going to go absolutely crazy and random looking after this. But for the moment, well, I think most people would probably say that the first one does not look especially random. Yes, it's all zeros. And perhaps if asked why, you would say, well, it's easy to describe it. You might say, I know exactly what's coming next. It's very predictable. It doesn't look random. It doesn't match our intuitions for randomness. Then you might look at the next one. And I think you might say very much the same thing about it. You know what's coming next. If it keeps going in the pattern you think, you can extend it as long as you like. You can keep predicting it. If there were a casino game where you were told to bet on it, and you could, double your stake if you guessed right, you feel that you can make a lot of money very quickly. The next one looks a little bit more random, yes? It doesn't look, you aren't quite sure what's coming next. The first 6 bits you can somehow see, they make sense. But after that, the blocks of zeros and ones seem to go a little bit haywire. So that you might say that if one of these 3 is random, it's the third one. But now, what if I suppose that there's a binary point right there, like a decimal point, and so that's a fraction or a number. And now suppose I convert that into decimal. 0.14159, 2, 6, and at this point some of you might have a guess about what might be coming next, especially considering that we all celebrated Pi Day last week. So now the question is pi random, perhaps? And the temptation for most mathematicians is to say, of course pi is random. It's normal. It's got to be random if anything is. But now, let's remember the way that I argued to you that the first 2 aren't random. They're predictable. You know what's coming next. And many departments have someone that can recite pi to an incredible number of decimal places. Anyone in here?
We haven't find yet anybody.
Okay. Well, I gave pi to the right number of decimals such that the next one is the last one I know, it's a 5. But the idea is that maybe this isn't random because you could run, if you want to know the nth digit of pi, you can write a computer program to give it to you, right? So maybe pi isn't so random. You can compute it precisely, well, as precisely as you like, like before. So I always like to turn things on their head first by saying that the most random-looking number you can think of is not especially random. And in fact, I would claim that any number you can think of is probably not random, because if you can think of it, you can probably say what each bit of it is, what each decimal of it is. So now I'm going to go through a bit of an explanation of what we think randomness should be. Then I'm going to formalize the definition of it. Then I'm going to formalize the other part of the title of my talk, the notion of computational strength. And then I'll start talking about how these two ideas play together. It turns out that, depending on your perspective, they either play together extremely well or extremely poorly. And I'll talk about those perspectives. So, let's start by trying to define randomness. And the first attempt you could make, and this might sound a little bit familiar to those of you that I was talking with at 1 o'clock, is that an infinite binary sequence is random if it doesn't have any rare measure theoretic properties. If in some way it looks measure theoretically like almost everything else. And that seems to make sense. Certainly the things that I described are very rare measure theoretically. They're the things that have precisely those approximations that you think they have. But there's a problem with this approach, and it's that if you look at it that way, everything is going to be random, because every sequence is definable precisely by a very rare measure theoretic property.
Nothing will be random?
Yes, it does. You just have to insert a couple negations in the right places, and everything is perfectly fine with this slide. So, if this is the worst thing that happens today, I just really good. So, alright. So yes, the problem is that nothing will be random because every sequence has a very rare measure theoretic property, namely the exact sequence. You can't get much more measured zero than that. And, well, this is a rather a problem for the first attempt. So then what we might do is we might say, all right, we like our basic idea. Our infinite binary sequence is random if it doesn't have any rare measure theoretic properties of a certain kind. So we don't want to avoid all rare measure theoretic properties because we've seen that before. We just want to avoid a certain kind of them. And the discussion about what that certain kind should be goes back many, many years. It hasn't been studied especially constantly for those many, many years. There were attempts in the 40s, an actual definition in the 60s, pretty much no attention paid afterwards to it until the late 90s. But now there's actually a reasonable way to look at this, and it's through the framework that both Wesley and I use for the world, which is that of computability theory. So that lets us calibrate randomness and say formally what properties we want to avoid, what properties we don't care if a random sequence avoids. So the basic tool we have is a partial computable function, and I could define this formally and we would be here for a very long time. Or I can just say, pick your favorite programming language, or least favorite, as the case may be, and just think of a partial computable function as a program in that language. And maybe the point I should make now is that there aren't very many of these functions. There ought to be countably many, I know where my head is, because how many computer programs are there? Countably many, right? And it also tells you that I'm going to work in a somewhat limited universe. I'm going to consider that anything you input is going to be a natural number. Anything you output will be a natural number or something you can code in a reasonable way by natural numbers. So we live in a very small but effective world. So we have countably many partial computable functions. And I should also point out why they're called partial, which is that computer programs don't always stop running, given the long input, right? I'm sure that most of us have written a computer program that doesn't always halt, even though you would maybe like it to. So I'm not putting any restrictions on how good the computer program has to be. Partial computable functions can be very bad indeed. And I drop the partial if it's total, essentially. If no matter what you input, you get an output. So it might take you a very long time to get an output. There are no time or space limitations on this computation. But you will get an answer someday, or perhaps your grandchildren or your grandchildren's grandchildren. There will be an answer at some point.
One answer.
Sorry?
Unique answer.
One unique answer. Once you get an answer, the program will stop. So then, that lets us define computably enumerable sets, which are quite well named. They're subsets of the natural numbers, and they're ranges of computable functions. So you can see how a function like that could enumerate a set, right? You have a function f. You input 0, you get an element of the set. You input 1, you get another element of the set, so on and so forth. So essentially, you have a program, and it starts listing off all of the elements. And you can think about this also as if something is in the set, eventually you find out. Because eventually it will be in the range, and once you compute f of that thing, you know that that is in the set. What if, say, 5 isn't in the set? You're never actually going to be sure as you start computing the set, right? All you know is that it isn't in the first 4 elements of the range, it's not in the first 5, it's not in the first 6. But even if it's not in the first million, you'll never know that it's not the value of f the million of 1. So maybe the way to think about this is eventually, if something's in the set, eventually you'll find out. If something's not in the set, well, good luck with that one. And the first main definition I'm going to use for randomness is in terms of avoidance of intersections of RE sets, CE sets. I'm trying to speak the language that Leslie uses, which is to say computably enumerable and computable. I grew up saying recursively enumerable and recursive. It might slip every once in a while. Leslie uses, I guess, lovely modern technology. So, let's see how I can do this. Well, a Markov test, which is the way I'm going to define these intersections of CE sets. We're going to take a sequence of open sets in the space of infinite binary sequences. And this sequence of open sets has to be definable by one particular computable function t. And the measure of each one of those open sets, the I open set, has to be no more than 1 over 2 to the I. It could be less, it could be equal, I don't care. But there's an upper bound on the measure. So let's see how this works. What's going to happen is that P takes in some input I, and once P takes in I, that starts the machinery whirring in this computer program, to mix metaphors horribly, and P starts outputting that this sequence of finite binary strings. So normally I would say it should be outputting natural numbers, but you could code finite binary strings perfectly well by natural numbers. Just list them out very nicely, graphically, but list them out nicely by length, and assign, say, the first one 0, the second one 1. So if the output's 1, you read that as signal 1. So how should this work? Well, let's say that in my space of all finite binary strings, maybe this string is sigma 1, maybe this string is sigma 2, maybe this string is sigma 3, and vi is going to be all the strings that extend sigma 1, all the ones that extend sigma 3, all the ones that extend sigma 2, and then maybe when sigma 4 goes into the set, we add in all the strings that extend that, so on and so forth. So each of these gives us a basic open set. Vi is the union of all of those basic open sets. And the list of basic open sets for each VI is determined by a computer program. So we say that the sequence is random if, remember I said we want to avoid a certain selection of measure zero properties. Well, how do you get a measure zero property out of a shrinking sequence of sets? You take their intersection. The measure of that intersection can really going to be zero. And we say that the sequence is random if it's not in the intersection of any such test. So you could think of each of those tests as V1 provides some guess and measure no more than 1/2 where that sequence could be. V2 does a better guess up to 1/4. V3 does a better guess up to 1/8. And if no sequence of sets like that can actually capture then A is random. It can't be caught. It can't be zoomed in on in this way. So I think the most sensible thing to do at this point is to try to get an example. A sequence that is 0 at every odd numbered place is going to be random. So even if you don't know exactly what the sequence is, you know that the odd places are going to be zeros. Well, let's see how this works. So what's V1? Well, we get the string 0. So everything above the string 0 is in V1. That has measure 1/2. Then what about V2? Is everything that is 0 at the first place and at the third place. So we could have 0, 0, 0, and V2 contains this, or 0, 1, 0, and V2 must also contain this. So V1, everything that must have 0 at the first place. V2 is everything that has 0 at the first and third places. And we can see we're adding 1/8 plus 1/8 to measure 1/4. And then we keep repeating this over and over. V3 is 0 at the first 3 odd numbered places, so on and so forth. And you can imagine writing a computer program that would give you precisely this sequence, right? If you write, if you give it I, you can just say, I want the first I odd places to be 0, and I want every combination of 1s and 0s for the even places. You can do that. So no sequence of 0 in all odd numbered places is modulo random because I've just written a text that wraps every single one of them. Every single one of those will be in the intersection here. Okay. So that's the basic idea behind randomness that I'm going to be using. You can't narrow in on it using PE sets in this way. So now, I've calibrated randomness. Maybe I should calibrate the other half of the title of the talk, computational strength. So we say that a set C is computationally stronger than a set A if there's a partial computable function that can always tell whether each n is an A, no matter what n you ask about. It'll always answer yes or no, but you let it use B as an oracle. And this is why I'm supremely glad to have a talk with this room. Because my ability to do this in LaTeX is very limited. So we have a question. The question is whatever n you want to know is n in A. So then we ask our program P. And our program P might do some basic computations, and maybe that's all it will need, and then it will return maybe 1 for yes, 0 for no. Or maybe it will say, to answer this question, I need to know whether 17 is in B. And if I know if 17 is in B, I can make more progress towards answering the question about that particular thing in A. So we have an oracle, P, and what P does is it places a And P asks over the phone, is 17 in B? And the oracle checks B and says either yes or no. And then P goes on with the computation. And then maybe later in the computation, P says, well, I would like to know if 50 is in B. So it makes the phone call again. And if P can do that with only, say, finitely much access to B, because, phone companies get annoyed if you place infinitely many phone calls. If P can do that, and in some finite time, placing finitely many phone calls to B, either come back with yes or no, no matter what the end you're curious about is, then B can compute A. So maybe the quickest example is if you're given B, and you want to know if n is in B complement, what does the computer program have to do? Well, if I ask you if n is in B complement, P just goes off and asks B, is n in B? And if the answer that B comes back with is yes, he says, well, no, it's not in B complement. And if the answer that B comes back with is no, he gives you the answer, well, yes, of course it's in B complement. So that's perhaps the easiest example here. But that's how we say that something is computationally responsive. You've got a computer program. You could make finitely many phone calls to the oracle. And in this case, if this works, we can say, well, B is stronger than A. If you know B, you can get A. And we say that B term computes A. And of course, it's possible for two sets to be equally computable, right? If you know B, you know A. If you know A, you know B. The B and B complement example is precisely the easiest one I can think of, other than B is equivalent to B, right? There you don't even swap the yes, no. So this lets us define equivalence classes of sets that have the same computational strength. If A can compute B, B can compute A, they have the same Turing degree. And the Turing degrees are an incredibly rich, complicated structure. And I'm going to not talk so much about them, but I'm going to mention one very important set. And that very important set, I realize I'm erasing a work of fine art to draw a picture of the Turing degrees, but that very important set, it's called zero jump for reasons I don't care to get into. It's the Halton set. You can list all of the computer programs, and if you want to know if the X program halts on input Y, that set will have the answer for you. Obviously, this is something that you can't always tell just by looking at the program. You have to actually run program X on input Y and wait to see if you get an answer. But there is a set that has coded into it exactly those pairs that make that thing halt. Exactly the pairs where the X program halts on input Y. The wrangle is just the standard pairing function. Take your pick for your favorite way of pairing natural numbers. That's it. So zero jump is the Halton set. It can answer all your questions of, if I give this program this input, will I eventually get an answer someday? So that's not going to be computable, by which I mean no computer program can answer that question without an oracle. Because if the answer is yes, obviously there's a computer program that will find that out for you someday. But if the answer is no, I promise you that there's no computer program that will tell you when the answer is no. So this is I don't want to say it's a very strong set, but it's not the weakest set in the world. So we have 0, we have at the bottom, you can think of that as the sets that you don't actually need oracle access to ever figure out is something in and something out. So for instance, the primes. A computer can always tell you whether something is prime or not, right? It doesn't have to have access to an oracle. So say 0 is the prime, the even, the empty set, all natural numbers. Things you don't need an oracle to figure out, zero jump is somewhere higher up. And why am I talking about that particular set with respect to randomness? Well, Kuchera showed in 1985 that if you have a Turing degree that computes zero jump, that's stronger than zero jump, or equal to it, I guess, then it has a Martin-Lafreniere sequence. So this gives us a giant class of things for randoms with. And then Frank Stefan, my first postdoctoral supervisor, showed, well before I became his postdoc, that any Martin-Lafreniere sequence that computes a complete extension of piano arithmetic also computes zero jump. So what he showed essentially was that there's something very special about the Martin-Lafreniere sequences that compute zero jump. That's one way of saying they're computationally strong. They can always solve the Halton problem. As getting Martin-Lafreniere sequence up here, this program X solve on input Y, well, it's strong enough to compute zero jump. It can always give you an answer. What Stefan showed here was that those are also strong in another way. They're strong enough to take the incomplete theory of piano arithmetic and find a consistent, complete extension of it. So that says that gives some sort of robustness to the class of random sequences. That compute zero jump, they're computationally strong in two very different ways. So let's look at maybe some intuitions that people have about randomness. What should you do? Well, what does it take for a sequence to have high computational strength? Well, the first thing is that it should have information content. Saying that, say, finding out what the even numbers are is not a whole lot of information content. Finding out which program halts on which input is more difficult to find out. It has higher information content. But that is only useful in terms of having computational strength if that information is organized enough to be retrievable. Because otherwise, what you're going to have is someone calling up the oracle, and the oracle saying, wow, I can't find a piece of paper that tells me whether 17 is in D. I've got to get back to you later. And then it never calls back because it's embarrassed it can't find the paper. So, the sequence has high computational strength if essentially those two things hold. And one has the idea that random sequences should have lots of information. They should be hard to describe. But if I tell you that a random sequence should have organized information in it, all of a sudden that sounds trickier. So this suggests that a random sequence should not have high computational strength. But they do, a lot of them. So every degree above here has a random sequence. So the question is, maybe those aren't the real randoms. So the question became, well, there are random sequences in every Turing degree up here. But there are also Turing degrees outside that cone that have random sequences. Can we just talk about that as a different kind of randomness? And, well, maybe I should bring up an analogy here, based on an analogy that our colleague at Chicago, Dennis Hirschfeld, always mentioned, and I'm quite likely to use my own, in the what does it mean to be random sense. So, let's see, I understand there are quite a lot of local elections coming up this spring, let's discuss Carbondale City Council, some other stuff. And suppose that someone wants to give random answers when asked about the local politics. Well, there are two ways to do that. The first and most obvious way is the way that I would do it. I don't know anything about who's running for Carbondale City Council. So if you ask me questions about that election, I'm going to give you random answers because I have no other way of giving you any answers at all. But I imagine that there are people in this room who are much better informed than I, and who could make their answers appear random because they would know what the correct answers were. And by strategically answering correctly or incorrectly, you could give the appearance of not knowing anything, just like me. You wouldn't be right too often in a row, you wouldn't be wrong too often in a row, you wouldn't be more right than wrong, more wrong than right. You could calibrate your responses precisely. So the analogy that I'm trying to make is that these are the two kinds of random sequences. The ones that can't compute zero jump and that are like me in terms of politics down here. If they're random because they're purely random. But these ones with high computational strength, well, maybe those are just pretending to be random in some sense. They know how to answer the questions right. So they're random because they're faking it, more or less. So that makes characterizing the randoms that are somehow truly random an interesting project. And, well, that means that maybe we need a new kind of randomness. Maybe Martin-Wolf randomness isn't cutting it because, well, there are all these computationally strong ones out there. So how could we alter the definition to get something stronger? Well, the first thing that you could do is you could say, to be random, you have to pass more tests. You can't just pass the Martin-Wolf test, you have to pass more, and maybe that will mean that you're the random sequences that aren't computing zero jump. And the first way to do it might be to say, well, what if I don't have to have that particular bound? I don't have to say that the VIs go down to, your measure goes down to zero at a certain fixed rate. Maybe I just say it has to go to zero in some ways. Maybe I can't ever tell how fast it's going to be. This gives us something called mean-to randomness. And that is a stronger notion than Martin-Wolf randomness, because if you're weak to random, you not only have to pass the tests that go to zero at that special rate, you have to pass all the tests that go to zero at all. So it's harder to be random. That's a stronger notion. The next one is the one that's most annoying to explain, but I've got to do this anyway. And the idea here is that before, remember, the function that is defining VI is fixed. So it says, I'm going to start, if you give it I, it says, I'm going to list the things that give you VI, and then it doesn't change its mind about any of them. Once it lists sigma 1, everything that extends sigma 1 goes into VI. But here what we do is we say, well, we're going to let this function say, oops, I thought this was VI, but it's really not. So what's happening here is maybe it starts listing VI, sigma 1, sigma 2, sigma 3, and then it says, wait, that's not what I want for VI. VI is now extending tau 1, tau 2, tau 3, so on and so forth. And then maybe it changes its mind again, and again. But what I'm going to do is I'm going to balance the number of times it's allowed to change its mind, because otherwise this gets entirely out of hand. And so I'm going to choose some computable function, maybe say 2 to the I, and I'm going to say that we can change our mind about VI 2 to the I times. So we're allowed, say, so for say V1, we're allowed 2 mind changes, so we start listing off V1, and then we say, oh wait, that wasn't it, let me have a second try at it. For V2, we could say, well, okay, I'm going to start listing off V2. Oh, wait, I made a mistake. Now I'm going to list V2 in this way. Oh, that's not it either. I'm going to list V2 in this way. Oh, that wasn't it either. And then that one last way, it has to stay there. Of course, it doesn't have to change its mind that many times. Maybe V2 stays as it originally was the whole time. But you'll never know. You'll be on the edge of your seat wondering, at some point, is something different going to happen? So, clearly this is going to give you something stronger, because you not only have to satisfy all the tests that never change their mind, you have to satisfy all of these mind-changing tests. And then you also have a different passing condition. Don't worry about that. It's still stronger. So you have Demuth randomness down there. And then finally, we could say, well, why don't we let this program that's defining randomness have Oracle access? Why don't we say, does the halting set think something is random? And that gives us something called 2 randomness. You could guess also that there's a 3 randomness somewhere in the world and a 4 randomness, and you would be right, but I don't care about those right now today. The only thing I'm going to, and I hope I'm not writing this too far on the board, I probably am. The only thing to keep in mind is that 2 randomness is the stronger of both of those. Weak 2 randomness and Demuth randomness, they're strictly between those 2 in strength, but they don't, neither is a subset of the other. You have weakly 2 randoms that are Demuth randoms, there are Demuth randoms that aren't weakly 2 randoms. And now we can say, well, are any of these what we're looking for? Can you say, of those 3 things, are any of them precisely the ones that cannot compute 0 jump? And the answer is going to be no. Don't worry about what everything in here means, but I'm simply pointing out that this is a cottage industry at some point. If you have a notion stronger than marginal randomness, it's fairly standard to try to say, these are the marginal randoms that cannot compute insert things here. And for instance, some of them can't compute certain kinds of CE sets. Don't worry about what those are made of. Maybe to get some kind of timeline on these results. These were done for Downey, Weber, and Hu results, and the Stefan and Triffine results were done maybe 8 years ago-ish. And the other 2 have been, along with the David results, and the other 2 have been done in the last few years. So this is within a decade or so. But there was still this gap. Those things turn out to be too strong. So I'm going to talk about a way to define precisely those marginal random reals, the ones that cannot compute 0 jump, which, as you can see, is easily the simplest thing that one cannot compute on the board. The rest all seem to be a little bit manufactured. And the idea here, if you remember the definition of Demuth test, I said that the Demuth test, you're allowed to change your mind about what CE set you're going to use to define VI. And you're allowed to change your mind up to f of I many times for some computable f. So here, essentially, we're not changing the whole set. We're taking things, we're putting things in the set, and then we pick them out. So for instance, a CE set, what do? You say, this goes in, and this goes in, because you're listing off the range of a computable function. For an NCE set, what can you do? You put the things you think are into x1, and then maybe later you change your mind about one of those, so you put that into x2. And then maybe you change your mind again, you decide you want it back in, you put it into x3, you can take it out again, put it into x4. But the number of times you're allowed to change your mind isn't bounded by some arbitrary function, arbitrary computable function, 2 to the I, 5i plus 12, 2 to the 2 to the 2 to the I. You're limited by some fixed number, and that number is the same every single time. So that's what an NCE set is. You're allowed to change your mind about whether something is in the set up to n times. You aren't required to change your mind n times, but for any given thing, you're allowed to change your mind about whether it's in or out up to that many times. Just like for the Demuth test, you're allowed to change your mind about what the set is up to f of I many times. So we have this NCE idea. I'm going to make my life far easier and write it like that instead of with all the unions and intersections. So you could just think of these as things you put in once, things you put in and take out, put in, take out, put in, so on and so forth up to N. So then, what my colleague and I asked was, how do we define an NCE Martin-Wolf test? And we thought of two obvious ways to do it. And one of them turned out to be equivalent to randomness. So not only is there not a new notion, it's not the one we want. But the way that we ended up doing this was saying, well, each VI should describe an NCE set of basic open sets. So each basic open set can enter and exit n times, no matter what set of strings you use to say it should go in and out. So let me, I think that this tone is not doing anyone a great deal of good right now. So the idea is that maybe, say, we decide that this string sigma goes in. So if sigma goes into, say, let's talk about a 2RE set. So what does that set look like? X1 minus X2. So maybe if X1, if 0, I can't read my own writing, if sigma, and here's X1. Well, now we think that everything about sigma is going to be in that component of the text. But then maybe if we put sigma into X2, we erase all this from the text. Or maybe if we put, say, tau into X2, we don't erase all of sigma from the text, but we erase the bit about tau. So for each basic open set, we can change our minds for here twice. If I made this 3RE, I could put anything in tau back in once, but then I'd never be allowed to take it out. So we've got a very firm limit on the number of times we can change our mind about, does this open set go into VI? All right. So this is essentially exactly what I just said, but with a lot more subscripts. I'm going to slide right through. Basically, you're allowed to put, for each VI, you're allowed to take things in, put them out up to n times, and we're going to keep the measure condition going. So at the end, there is an end, but as you go along, your measure will not be more than 1 over 2 VI for the I component, so the intersection still goes 0. And we say that something's random if it passes every test like that. Well, basic facts. 1, CE randomness is Martin-Wolf randomness, because you just put things in, you never change your mind to take them out. And the other thing to notice is that every n plus 1 CE set is NCE random. N plus 1 CE random is already NCE random, because now you not only have to pass the n tests, you have to pass the ones with another component. So now we have questions. Are all of these notions different? Is Martin-Wolf different from 2 CE? Is it different from 3 CE? Do some bits of this collapse? That would be nice. And it turns out that the answer is yes, if n is at least 2. So don't worry about the proof. The general idea is that if something fails to be NCE random, then it already failed at an earlier point. So it already failed to be n minus 1 CE random, or it failed to be Martin-Wolf random, or it failed to be n minus 2 CE random, or it failed to be 2 CE random. So this tells you that for 2 on up, it doesn't matter which n you use, which is really nice, because it means you can just use 2. And that's why I'm going to start calling these sequences difference random, because all that matters is that you'd be allowed to take a difference effect. Whether you add something in or take another difference, I don't care. But one difference is all you need. And I can also say that it's a proper subset of the Martin-Look random sequences. One could compute very quickly a Martin-Look random thing that is not random. And it turns out that where they fit in this is exactly where you hope they fit. It's being difference random is stronger than being Martin-Look random. It's weaker than both of those. This is good. It's just about what we're hoping for. And it did turn out to be exactly what we were hoping for. So, I should say that this wasn't what we were going for when we started studying difference randomness. We just thought it was cool. And then we found out that it actually solved a problem that a lot of people wanted solved, and we were very excited about that. So, let's see. The way one shows this, I think I can give a bit of a flavor of it in the next couple minutes, is that for difference randomness, you allow yourself to change your mind. You've got n different CE sets for less than 2, right? You have 2 different CE sets, and you can say in this one, if it goes in, you can say in this one and in this one if you want it out again. So what we can do is we can take the Dennett's test and use that to characterize difference randomness. And the idea here is that for most Dennett's tests, you could always go backwards. You could take one thing that would define BI and then you could change your mind. But those might have overlap. You might have done a very bad job changing your mind, and they might actually be the same set. The Dennett's test is strict if whenever there's a mind change, the new version has nothing in common with any of the old versions. So if, say, all the strings extending sigma go into the Dennett's test, the first attempt at BI, then if you change your mind, nothing extending sigma will ever go into a later version of BI. So once you change your mind, you've changed your mind about all the open tests. And what we did to show this was basically to use this characterization of difference randomness as passing straight Dennett's test. And the way we did this, one direction is not especially interesting, the other direction is the fun one. So what you do is you assume that A is Turing complete, which is computability 0 speed for compute 0 jump, computes the Halton set. And we want to show that that thing is not difference random, meaning that you can catch it in either a difference test or that kind of Dennett's test I just described. And, okay, I don't really have a chance to get this, but we just say that it uses a lovely little black box that if a recursion theorist or computability theorist claims that he or she understands it, either they're lying or they really don't, or they're never going to be able to use it properly. It's a lovely little theorem, kind of like a fixed point theorem. It basically lets you build something knowing exactly what you're going to build, except you know how to build it, you know you're going to end up with the right thing, and you don't know what the right thing is yet. So it's kind of a cute little proof. And the other thing I want to mention very quickly is that Selvin, my colleague, and I added another line to that table by saying, well, what if you let yourself change, instead of having some fixed n, so 2, CE random, difference random, what if for each I you let yourself change your mind, say, 2 to the I many times, or 3 to the I many times? So for V1, you would have x1. For V2, you would have x1 minus x2. For V2, you would have x1 minus x2, and x3 minus x4. And then you would go on to 8 possible mind changes for V3, 16 for V4, so on and so forth, and say you have to pass all tests like that. And we call that omega change random. And the only thing to say is that it falls into this little block here. So if I were still editing this, I'd stick it in between those guys. And it fits into table very nicely as well. So we thought that this was fun, a nice project. Again, we didn't go for what are the things that are marginal of random that can't compute strongly constant sets, but we found them. And I think that this adds something very nice. If you have a stronger randomness notion, you can say these are the marginal of randoms that can't compute what. So like I said before, the theory of the Turing degrees is very rich. There are lots of different kinds of Turing degrees, different ways of saying they're strong and they're weak. So maybe the question is, we can say things are marginal of random and they can't compute such and such. Why not try to find a definition of randomness that matches up with that? And there are also, when with the study of randomness comes the study of being really, really not random. So strong randomness notions so far have been shedding light on what it means to be very far from marginal random. Maybe more things of this ilk would be able to show us even more, because the things that are far away from marginal random are easily the messiest collection of things that are far from insert object here random that I know of. So I think there's a lot of fun stuff to do. It turned into a really nice project. And, well, I think at this point all I can say is thank you for listening.
Other questions?
So this notion of Demuth randomness that we used, this whole notion of changing one's mind that makes me a bit queasy. And
Fair enough.
Because so P sub I can change its mind up to F sub I times.
Mm-hmm.
How? I mean, are you introducing a kind of random variable there?
No. Okay. So essentially, what is the program that defines, say, a Demuth test? What exactly is it doing in there?
Yes.
Well, you could think of it as computing let's say, T. Oh, that's lovely. So, the idea here is that if you have, say, a Markov test, this, you just need PI, it always gives you the same value.
Mm-hmm.
But for a Demuth test, you calculate PI1, and maybe that gives you a value, PI0, and maybe that gives you the value, say, 2, and it says compute the second use function 2 to spit out its range as your PI. And maybe PI1 is still going to be 2. PI2 is still going to be 2. PI3 still 2. But maybe at maybe at 27, all of a sudden we decide that spitting out the range of the second function is not going to give us the VI we want. Maybe we decide that we want to use function 1724. So you could think of this as it's still a computable function. It's just a function that's allowed to change its mind about its value. And so it says at time 0, I think this is the right set. At time 1, I think this gives you the right set. At time 27, I no longer think 2 gives you the right set. I think 1724 does. And this is still going to be a perfectly recursive function, computable function. It's going to always give you a value. And there are only going to be, say, if, say, you're allowed to, say, let's say 5 mind changes, there are only going to be 5 points where the values of PIT and PIT plus 1 are the same. So does that make sense? Feel more comfortable?
Somewhat.
Fair enough.
Because now it seems these indices might be right, the places where these things occur, right? You know what I'm saying? So in other words, how did we come up with 27? You know, where it decided that's the place where it changes its mind. You see what I mean? So now the mind changes are the mind changes are now deterministic, right, or computable,
Yep.
right?
Are they computable? They're
No,
computably enumerable.
they're computable enumerable.
Right, I'm sorry,
yes.
If you know all the places of the mind changes, you know the
You
whole
just
limit
know.
function.
Because
Right.
you just go straight to the last mind change and you just relax.
Right.
Okay.
Okay.
So it's like a computable function
Right.
gives you a CE set as its range.
Right.
This computable function gives you a CE list of mind changes in some way.
How do the concepts change with the measure mu? If you play around with the measure, do you preserve the structure or not?
So in some way, so it doesn't affect the basic theory. You could see that there was nothing contingent on me using a particular
No, I
measure.
mean if you use a
If I
different
use
measure,
different, yeah,
can you confuse?
then you're going to get perhaps a different set of things that are random. There's actually been quite a lot of work done by my advisor and the second most recent postdoc on the subject, actually. If you switch the measure in this certain way, how different are the random sequences? And in what ways can you shift the measure around that give you something that no one in the world would think of as random? So yeah, there's a lot of very nice stuff going on there.
Okay.
And the thing that you really don't want is measures with atoms, right?
Yes.
That's
In absolutely continuous measure together, then
Yeah, yeah,
have
and
to get
like-
the same answer.
yeah, you would like something continuous, you would like something that's computable. I'm not going to try to code their work because I know I'm going to get it sufficiently wrong to really be an interesting.
All right. We hope you all can join us for some refreshments upstairs in the 3rd floor math library. Thank you, Johanna.
Thank you.